Hello and welcome to this part of Advanced Materials Chemistry course. This is the second lecture and we will quickly recap what we learned in the last lecture. First, what are the semiconductors we came to know. Then little bit of the elemental and compound semiconductor materials. Mainly elemental materials are silicon and germanium, and compound elemental materials when two or more elements are added and the resultant compound behave like a semiconductor, then we call them a compound semiconductor materials that can be binary, ternary, quaternary kind of things. Then we studied or we learned some important crystal structures which are necessary to learn the some important crystal structures which are relevant to the semiconductor physics. So these are mainly the closed pack structures, FCC and HCP, and we also learn on the tetrahedral voids. What are tetrahedral voids? We can just once again quickly one can see. So suppose we consider atoms as sphere. So we have three spheres of one layer. There is a long layer and you have three spheres. And then above this we can put one, suppose for the time being a small sphere. And then you put another sphere above that. And now you expand the middle sphere to the sphere of the same size. So what we get is the actually a diamond structure, and the angle will be 109.47, which we all know from our basic chemistry. Then we learn diamond and zinc blende structures for semiconductors. Diamond and zinc blende structure has one difference, that in diamond structure, both the atoms, there are two interpenetrating FCC structures in both of them. However, in diamond structure, both these lattices are consisting of same atom, same sphere, like silicon, and carbon. And in zinc blende structure, both interpenetrating FCC structure has two different elements. Like in gallium arsenide, you have an FCC structure of gallium, and then the another FCC structure is of the arsenic. So here, suppose in this example, if I will say, so all these four spheres will be of gallium, and inside which we saw the red color, that will be the arsenic. Then we learn little bit of the crystal plane, because this plays a very important role when you want to actually make a device. The properties of different crystals, or when we say anisotropic, there are some anisotropic properties which are, you can say, depend on the crystal planes. So that is the reason why knowing the crystal plane is very important. Then we learn of the valence bond, that all of us was already knowing. Then formation of energy band, how the energy bands are formed when we have an atom, how it behaves, and when we bring many atoms together in a, you can say, in a crystal, where all the atoms are arranged in a definite fashion. So then the bands are formed because of the overlapping of the orbitals or overlapping of the wave functions of the electrons. And then this was a general energy bands. Then we in detail we studied how the bands are formed in the silicon. Now with this there are some important concepts also we learn, and we will know some more concepts during these slides, which are essential for semiconductor physics, or in order to use semiconductors in a device in a proper way, we need to know some of these concepts. Number one is that electrons are responsible for the conduction. This is very sure, especially in solids. In liquid, ions are also there, but for our purpose, for the time being, we will say electrons. Now, you have an electron which is having a very less mass. So when it start moving, we know that every particle, when it is moving with a momentum v, there is a de Broglie wavelength associated with this. It behaves like a wave. So because the mass of this electron is very low, so the wave nature is dominant, even if it start gaining energy slightly higher. So when if the mass of the electron is me, in that case, the energy of that electron can be given by p square by 2m. And p is the momentum, and momentum we know is m into v. Now next comes the de Broglie wavelength. De Broglie wavelength for any this moving electron, or you can say any moving particle which is having momentum p, can be given by this formula, where lambda is equal to h by p, or we can say h upon lambda, h cross upon lambda, where h cross k is another way of representation, where k is a wave vector, and it is given by 2 pi by lambda. See, wave vector and like momentum, these are interchangeably used in solid state devices or in quantum mechanics. So k is generally preferred as it is independent of the mass. K is we call is a wave vector if it is vector, and in general wave number. When an electron moves inside a periodic potential, its motion is influenced by the periodic potential. So if the electron, when the electron is free, you can give any amount of energy. By applying a potential, it will gain that. It is simple, E into V, the energy will be gained when you put an electron inside a two parallel plates, you apply a voltage or potential V, so it will gain energy equal to EV. But when it is inside a periodic potential, the things are not exactly the same. So all the energies, in the previous one, when the electron was free, it could have any amount of energies, but all the energies are not allowed when it is under a periodic potential. This I have also made another slide. We will see in 2-3 minutes. So then there are certain energies which are allowed, and there are certain energies which are not allowed. So because of subjecting this electron inside a periodic potential, we can control the motion of electron. Because now we know that if electron is moving inside a periodic potential, it will behave in a certain way which is different than the its behavior when it was moving inside, when it was free. So we can, and how we can change the periodic potential? By changing the lattice. So such infinite periodic potential can be readily provided by single crystals, because there are a lot of ions there. So in order to form a single crystal, when we bring many atoms together, then due to their mutual interaction, electronic energy bands are created. This we have seen yesterday, and in previous slide also, we just again reconceptualized. And so then we also learned that bands are of two types, which are valence band and conduction band. So the valence band is the highest range of energies, which means electron normally present at absolute zero temperature, while the conduction band is the lowest range of vacant electronic states. The bands are continuous for entire crystal. That means any electron in a conduction band belongs to the entire crystal. It is not like that in particular atom, if the electron is there inside that atom, it belongs to that particular atom. However, when it is inside a lattice, and especially infinite lattice, in that case, that electron, once it has gone to the conduction band, it is not particularly associated to that atom. It is for the entire crystal. Now there is one more thing you must always remember: the infinity is also you can say it is infinity, infinity also depends. Infinity means not in terms of distance. It can be like you are having one atom and there are within 1 centimeter there are 10 to the power 23 atoms. That can also be called as the infinity as compared to the single atom. So like one atom typically of few angstrom, and when it is inside a crystal of 1 centimeter, in that case 1 angstrom compared to 1 centimeter, you can always call 1 centimeter as infinity. Presume. So presence of electron in the conduction band plays crucial role in the properties of substances. So insulators have electrons in conduction band, and insulators hardly have electrons in the conduction band, and conductors have plenty of them. So it is difficult to control and regulate the flow of electrons in these substances. Now we want to emphasize the importance of semiconductors. If you see insulators practically there are no electrons or very, very few electrons inside their conduction band. So their conductivity, electrical conductivity is very, very poor. On the other hand, if you go to the metals, all the electrons are, because the conduction band and overlaps, so all the electrons are ready to move, and therefore there are large number of electrons available. So therefore, because in one case hardly any electron, in another case plenty of electrons, so it is very difficult to regulate and control the flow. Flow is possible, but regulation is not possible inside these substances. And therefore semiconductors are very important, where we can have good property control by controlling the things, many things. Now one important thing, as I already said, that electron, when it is moving, it should be treated as a wave. And when it is moving, let us say this is a crystal, infinite crystal lattice, where there are ions, and consider the electrons. These are ions plus, you can say, core electrons associated with that. So there will be positive, because the outermost electrons we are considering somewhere outside, if we are treating that in this fashion. So or even if they are inside, so still the core, or you can say that can be treated as a positive ion. And I have an electron which is actually moving inside this periodic potential from this side to this side. So you can say, if I plot this here, it will see the positive ion, and accordingly it will attract, it will see an attractive potential. It is like this. Then it will come here and it will come. So the potential, if you drop along with this line, it will be kind of this. So suppose there are ions, and then the potential felt should be like this. We can make it approximate to this square potential, and this problem you must have studied in quantum mechanics. That is called as the standard quantum well. It is a quantum well, or in something some quantum barrier also, because if energy is low, then this part will behave like a barrier. So but here it is a well. So now you have an electron moving inside a potential well, and that is a periodic potential well. So you write a Schrodinger equation and solve this quantum mechanically by various approximations. So you will find the solution of this particular problem when electron is moving inside this particular you can say periodic potential. The solution will be like this, and mathematically if we say it is like this. No? So this curve, the left hand side I have drawn is like this, and the right hand side I have drawn above. So you see the right hand side, which is cos k, we know from our basic trigonometry that cos cannot have value more than 1. So if it is, whenever this curve is going above +1, or whenever this curve is going -1, in that case the solution will not exist. And therefore, these values, like if I bring it here, so from this value to this value, from this value to this value, and from this value to this value, the solutions will exist. But here, when the value, the left-hand side value is higher than 1, in that case, the solution will not exist. So this will be breaking. So these energies, if you see, this is a Ka. K is related to momentum. K is related to, in that case, you can call it related to the energy also. So in this case, where these values are above +1 or -1, because right hand side can have only value of +1 or -1, therefore this will not exist. This will put the restriction on otherwise a normal parabolic structure EK diagram, that is E, that is K. I will once again tell you in the next slide what EK diagram is. So you will see it is not now a continuous, because on these values actually there is no solution which exists. Ideally this EK diagram should be a parabola, but now you have several breaks because of this these issues, and this arises because of electron subjecting to a periodic potential. So this we have already, because of today we have already lost some time because of the internet connectivity issue. So I will not go much detail into this, but very quickly I will once again brief the difference between what is the atom and how it behaves when it is inside the crystal. So this we know, it is an atom of silicon. I have made for that only. So it has certain energy levels. So now there are 4 electrons in the outermost orbit, and then it has certain higher energy levels which are only allowed energy levels. So this electron can either be here, or it can be here, or it can be here. It cannot exist anywhere in between these values. This also we know very well. So if you give certain amount of energy to this electron, and this energy is only this much, so it is not going to accept that energy. It is going to accept only energy when this is exactly amount of this energy is exactly equal to this gap. So once you if any energy, it can be in form of photon, it can be in form of any other energy. So if you give it to that, it will absorb and it will reach to any higher orbit. And it cannot stay there for a longer time. It will immediately come back by emitting the same amount of energy. However, so if you give an energy which is suppose energy is exactly equal to this level, it will accept it and reach there. However, if energy is slightly higher than this, it is not the case that it will absorb this much amount of energy and the remaining amount of energy will be in form of kinetic energy, or like a general concept which is a wrong concept people are having in mind. So just make it clear that it can only absorb the energy when it is exactly matching with the energy levels. When you bring so many atoms together, so the situation is like here, it is a single atom. When it is a single atom, it will be following here. But when you bring any number of atoms, n number of atoms, n tending to infinity, and here 10 to the power 23 in 1 centimeter cube of the order of 10 to the power 23, we consider that also around infinity. So when you bring them together, all of them at this distance, they will behave like atoms only. When you bring them together, their wave functions start overlapping, and at this point they will start having a you can say band like this, where there is a continuous band from this point to this point, and if you move them further towards left, then these band further start to split, and 4n level are here and 4n level are here. So when a silicon crystal crystallize, its lattice parameter is 5.43 angstrom. It's a FCC structure, and this is actual value of the silicon. If I say there is an assignment which depends on which is based on this you can say figure. So if I have if silicon was crystallized, having the same, although silicon with all the properties same, everything same, and if it crystallized with you can say this lattice parameter, in such a situation it should behave like a metal, because here you will have 4n continuous energy levels, and electrons should be in the lower level. However, there the levels are available. Whenever you get little bit of the energy, they can they can increase the energy, which is also an allowed energy. So energies are quantized. It cannot like here. So this is also in the case of crystals also. When you increase the temperature, when they are not at absolute zero, in that case, the atoms or ions, they vibrate around their mean positions. So that vibrations are also quantized. This also, so you keep in mind. And those the vibration energies are also fixed. So you cannot have any energy between E1, E0 and E1, and E1 and E2, like here. E1 and E2 are only allowed. Similarly here, only certain energies are allowed. So these energies, according to this energy, this amplitude of vibration will depend on this energy. So the vibrational, when atom is vibrating, the amplitude of this vibration will also be quantized. So either it will be this much amplitude, or it will be this much amplitude. Suppose I say this is 1 centimeter, for example only. It is never 1 centimeter. But suppose I say it is 1 centimeter and it is 2 centimeter. So either it will have a vibrational amplitude of 1 centimeter or 2 centimeter. It will never have 1.5 in this particular case. So this is just the earlier slide which I tried to. So when it is in the crystal, the EK curve or EP curve is not exactly the parabolic like this. In the crystal, the curve is like this green one, and the curve is like this red one. This will be clear in the this slide also. So in order to understand this figure, and the earlier one also, there are energy momentum diagram which are drawn in the all kind of solid state or solid state physics, or in general the quantum mechanics, mechanical properties of these materials. So the energy of free electron is, we know, p square upon 2m0, and the p is the momentum and m0 is the free electron mass. So if we plot p here on this x-axis and E on this axis, so because it's a p square upon 2, we should get a perfect parabola. However, in a semiconductor crystal, an electron in the conduction band is similar to a free electron, though it is not absolutely free, because it is still inside a conduction band, and it will be free when it goes into the vacuum level. So above conduction band, there is a vacuum level also. Many times it coincide in some in many crystals, but in some of them it is slightly above. It depends on which material you are using. So in semiconductor crystals, an electron in the conduction band is similar to a free electron and is relatively free to move about the crystal. However, the periodic potential of the nuclei put several constraints, and E is equal to p square upon 2m0 is not valid. However, if the mass of the free electron is replaced with the effective mass, then the same formula can be used. Now there is a problem, because in earlier slide we see certain energies are not allowed. Why? Because of the solution doesn't exist. So if the solution doesn't exist, those many number of energies are not allowed inside a crystal. So what we can do, it will be a problem in that case, because we don't want to make the things complicated, and wish to keep the things as simple as possible. So we want to follow this formula. This is very simple, that energy is always equal to p square upon 2m. So what we do an approximation. So rather than taking this M0, this electron, we assume it's as a effective mass. We replace this M0 with an effective mass. So when it is inside this, then the effective mass is equal to the mass of free electron. However, when suppose inside those periods, those periods where the energy is not allowed, we can always say that this formula is always valid, energy is always valid to p square upon 2 m0. However, the energy, the mass has become infinite. So if mass become infinite, then of course that then we can assume that this curve is always valid. So then electron effective mass, it depends on the properties of the semiconductor. It can be obtained from the second derivative of E with respect to P. So you have this P and this E. So if you you can say this curve, if you can make second derivative, it is d2E by dp square. It and you can inverse of that will give you the effective mass. So now as the narrower the parabola, it will give a larger second derivative, that we know, because now the curve is very steep. So it will give a larger second derivative, and therefore when the parabola is narrow, in that case this effective mass will be small. And effective mass concept is very useful because it enables us to treat electrons and holes essentially as a classically charged particle. As I said, I will presume even if the electron is not allowed or cannot take that much amount of energy, it is not allowed to have that much energy, but I can still say that though it is having the energy, but its mass has become infinite. So now if you see the curve, normally in textbooks or in papers we see the bands which are flats. Okay, this is a conduction band, this is valence band, but actually it is not the case. The bands are very complicated in three-dimensional, and these are direction dependent, as I have already said. So suppose in case of silicon, if I say normally these bands or these energy diagrams are energy momentum diagram only. So if I say for a silicon, this is typical energy momentum diagram, and here the P is 0, and you will see the minima of the conduction band is not actually coinciding with the maximum of the valence band. We'll come to that later also. So the energy momentum relationship, also called energy band diagram. So this energy momentum relationship is only which is called as the energy band diagram. So for silicon it is here, and for gallium arsenide it is here. So we just try to visualize EP curve, these both the curves in 3 dimensions. So in like this is towards 1 0 0 direction, and this is it is in 1 1 direction. So it is not like the curve is not like XY. So you imagine from this point I am starting. So if I am moving to 1 0 0 direction, then it is this. If I am moving from 1 1 1 direction, it is like that. So it is very, very difficult actually to represent also that inside on a paper. So you just imagine 1 1 1 direction will be where it will be. So where okay, this is an assignment to you. You think inside a crystal of silicon, which direction is 1 1 1 direction and which direction is 1 0 0 direction. Then if you move towards 1 0 0 direction, you will see the band structure is like that, or EP diagram is like that. And if you move towards 1 1 1 direction, it will be like this. However, in case of gallium arsenide, you will see the structure is moving like this. So this picture should give should make it something clear in your mind that band diagrams are not always like this flat. There is a conduction band, there is a valence band. They are always curved. However, for a particular p value, for any p value, we can take those two values and then say this is energy, and that's why they look flat. So EP curve are shown here for two crystal directions, and since the periodicity of most lattices is different in various directions, the energy momentum diagram is also different for different directions, that as I already said. If the minimum of the conduction band occurs at p is equal to 0, this means the effective mass of the electron in every direction in the crystal is the same. It also indicates that the electron motion is independent of the crystal direction. Silicon, the maximum in the valence band occur at p is equal to 0, but the minimum in the conduction band occur along the 1, 0, 0 direction, and where it is p is equal to at this point, p is equal to pc. So this is the minimum, this is the maximum. So in silicon, when electron make a transition from the maximum point in the valence band to the minimum point in the conduction band, not only an energy change is involved, however, you also need to have a momentum change. So if there is a electron which is here, now you give certain amount of energy, so it will move from valence band to the conduction band. Now conduction band, it is the maximum. Either you can give this much amount of energy, then it is possible that it can move from here to here. But this is a very large energy. There is another possibility that you this is the momentum towards the direction, so you change, you give this much energy and then change in the momentum also. This you give, you change the momentum also. So in that case, you can give Eg energy plus change of the this momentum, and then the electron will reach into the conduction band. However, in case of gallium arsenide, it is the valence band and conduction band are lying at the same value of p, which is 0. So electron can easily, you can say easily take energy at this point and directly go to there. So here it's only the excitation energy sufficient to bring an electron from valence band to conduction band. Here not only you need an energy, excitation energy, however the lattice contribution also, which provides the change in momentum. And these kind of semiconductors where the momentum or the same momentum, both highest of the valence band and the lowest of the conduction band are coinciding at the same momentum, are called as the direct band semiconductors. However, if there is a difference between maxima of the valence band to the minima of the conduction band, those are called as the indirect semiconductors. That is, so like for gallium arsenide, the maximum in the valence band and the minimum in the conduction band occur at the same momentum, and this is called as the direct band gap semiconductor. So gallium arsenide is called as direct semiconductor, direct band gap semiconductor, because it does not require change in momentum for an electron transition from the valence band to the conduction band. It can directly go there. However, if you want to transfer one electron from this to this, in that case, you need to provide that much an amount of energy, and then lattice, this with the lattice, help of the lattice, you can provide this much change in momentum also. So thus an electron making transition from the valence band to the conduction band can do so without a change in the momentum. It is very fast because you don't require any contribution from the lattice, so only the incident radiation is sufficient. Therefore, it is very useful in the optoelectronic devices, and therefore if you see gallium arsenide is used in most of the optoelectronic devices. Now this we have already learned that double differentiating this PE curve or EP curve, this will provide the effective mass of the electron. Now Based on the band gap, we can differentiate the atoms or the materials in three different classes. These are metals, semiconductors, and insulator. One definition we saw yesterday, which says the conductivity, that metals have very high conductivity, insulators have very poor conductivity, and semiconductors have conductivity in between metals and insulator. Here we can visualize, or we can understand the difference in terms of the band gap. So variation in electrical conductivity of metal, semiconductor, insulator may be explained qualitatively in terms of their energy gap. So if you see partially the metals have either partially filled conduction band, or they have both valence band and conduction band, which are you can say the conduction band is inside the valence band. So now if you have an electron, this is the entire band which is allowed. You are having electron which is here, and you give little bit of the energy, 0.001 volt. Suppose you apply a potential of 0.001 volt, so energy will be raised by E multiplied by that voltage, and that energy is, you see here just above it, that energy is allowed. So it will, that electron will actually accept that energy and increase its own energy to that much. Now, so electron which was earlier here, it will move slightly at this point. Similarly, in this case also, when they are overlapping bands, in that case also, you see this is conduction band is up to this. This is also considered the entire one band, and then if electron is here at the top of this band, and you give slightly very slight potential, applies very slight potential, the electron will be able to accept that energy and will be increase its energy, and if it increases energy, in what form it will do? It will have a kinetic energy and will start moving. However, if we come in the case of, like, first we see this, which is an insulator. So suppose electrons are here. Now it is at the top of, it is holding that energy which is equal to the top of this energy, this band. Now if you try to apply a little bit voltage here, so suppose even 1 volt you want to apply, so the energy will be, or you can say very high. So the electron will try to gain, due to application of that high voltage, the electron will try to gain that much of amount of energy. And suppose it takes that energy like 2 electron volt or 3 electron volt. So if a potential is applied and that is sufficient to give an electron energy of 2 electron volt or 3 electron volt, you will see that the energy of 2 electron volt, it falls somewhere here, which is not allowed. So either this energy is allowed or this conduction band energy. So this is a gap where there is absolutely no energy is allowed. So this will not accept. So even you applied certain potential, the electron is not going to accept that energy, because it is not allowed to hold that energy, because that much energy which it is expected to achieve is falling inside this gap. So this is clear, and that is the reason why insulators, because they have a larger band gap, they are not good conductor of the electricity. Now the things is slightly different in case of semiconductors. So in semiconductor, the band gap, like I will talk about the silicon, the band gap is about 1.12 electron volt. Typically, the band gap, if it falls between 0.5 or even less to 3 electron volt, we call it a semiconducting material. So this semiconducting material, if you have, if you make it, if you put at absolute 0 Kelvin, it will also behave like insulator, that all electrons will be inside the valence band. as we explained yesterday. Now, when it is at the room temperature, what happens? This electron, these electrons which were at the you can say top of this level, because this gap is very low, nearly 1 electron volt. So few electrons having their thermal energy of even room temperature, which is though very less, but if you calculate the number of electrons in conduction band, with which the number it follows the Maxwell-Boltzmann statistics. So if you calculate even at room temperature, you will find that there are certain number of electrons which are available in the conduction band, and therefore it will give a little of the conductivity. As you increase the temperature, more and more electrons will reach in the conduction band, the thermal, because of the thermal excitation only. And those electrons which are already in conduction band, they can attain any energy, because all these energies are allowed. However, the similar situation cannot arise in case of insulators, because this thermally it is even if you calculate by Maxwell-Boltzmann distribution, n0 upon n upon n0 is equal to is proportional to e raised to the power minus e by kt, Eg by kt. If Eg is large, the number of electrons will be very less. However, if it is nearly in this range 1 to 3 electron volt, you will have a reasonable number of electrons in the conduction band also. So this was just a difference of metal, semiconductor and insulators in understanding on the basis of band diagram. Now we try to understand what is intrinsic and extrinsic semiconductors. So an intrinsic semiconductor is a pure semiconductor without any significant dopant species present. So if we take pure silicon and having a perfect which is crystallized in a perfect diamond structure, in that case this is called as the intrinsic semiconductor. There is no other impurity. So the number of charge carriers is therefore determined by the properties of the material itself instead of the amount of impurities. So you are not adding any impurity, and therefore the whatever are the properties of silicon, that will be the, or pure silicon, that will be the property of the your semiconductor. At the room temperature, the intrinsic semiconductor exhibits almost negligible conductivity, though they have little bit conductivity because of the thermal excitation of electrons from the valence band to the conduction band. However, at the absolute 0 Kelvin, they will be behaving like an insulator. This also you just keep in mind. So although semiconductors, the intrinsic semiconductors at room temperature have some conductivity because of thermal excitation, all the time at absolute 0 they will have absolutely no conductivity. However, extrinsic semiconductors are those that are result of adding an impurity to the pure semiconductor. So suppose you have a pure semiconductor and you add little bit of some other impurity. In silicon you add some other impurity like boron or phosphorus, and then because of you are adding an extra impurity, so some property of this atom will also be playing, you can say, a role in the final property of that semiconductor. But in this case, the semiconductor will be called as the extrinsic semiconductor, because now it is not a pure semiconductor of single or some, we have you can say added certain amount of impurity. The process by which certain amount of impurity is provided to a pure semiconductor is known as doping. This impurity addition is called as doping. Hence, a pure semiconductor is doped to generate an extrinsic semiconductor. Extrinsic semiconductors are of two types, N-type and P-type. This we will see. So, here in this slide we learned that there are two kinds of semiconductor. One is intrinsic kind of semiconductor, which are absolutely pure, there no impurity is added to them, and there are extrinsic semiconductor in which certain amount of impurity is added, and because of that impurity the property of that semiconductor changes. The process by which this impurity is added is called as doping. And this extrinsic semiconductor are two types, N types and P types. What are N types and P types we will see in next coming slides. Now because the doping takes place, now there are two kind of dopants. So when a semiconductor is doped with impurities, the semiconductor becomes extrinsic and impurity energy levels are introduced. This we saw in last slide. So let us try to see if I give an example of phosphorus. So imagine those three spheres. Now on those three spheres you are having all silicons, but the center one, which was the silicon, it has been replaced with the phosphorus. So now you have you have four atoms. I am talking about the tetrahedral void, three spheres which I showed in the first slide. So you have three spheres bottom, one sphere top, and one red color sphere which was small that was inside the tetrahedral void. So now initially all these were same. It was actually slightly above, the angle was also 109 degree. Now you replace one of them with the element phosphorus. So now what will happen? See, all these four silicons which were having 4 electrons, they will make bond of the 4 electrons of the phosphorus. Phosphorus has 5 electrons in the outermost orbit, but 1 electron will remain free. So what will happen? That particular void now we will have an extra electron. So now this phosphorus atom forms covalent bond with 4 neighboring silicon atoms, and 1 electron, the 5th electron, has a relatively small binding energy, and it becomes almost free. So it is, but it is not, still it is not free. It requires certain amount of energy to become free. So a level is actually created in between the conduction band and valence band, and this level is very close to the conduction band, slightly lower than the conduction band. You must have seen some lines there. So those lines, they are very close, so you require a very less amount of thermal energy to excite that particular atom from, you can say, from that level to the conduction band. And once it goes to the conduction band, then it start conducting. So now we can call it as a donation. Donation means that electron which was actually a part of, you can say, phosphorus, and which accordingly, because the phosphorus was doped, so a level was created, but that level was still below the conduction band. However, this can be donated to the conduction band. So that from there it comes as the donors. So the phosphorus atom is called as donor, and the silicon becomes N type because of the addition of these negative charge carriers. Now this when we are using when we are talking about the intrinsic semiconductor, extrinsic semiconductor, and the doping, so we and most of the students in the beginning of their career, they have a misconception that every silicon is now having a phosphorus atom which is not the nearby. This is not the case. This can never be the case. Otherwise, it will behave like an atom, like a metal. So it is not that the doping level is very, very, very low. It is in the case of ppm level. ppm level, if you understand, ppm level means about 10 lakh of such silicon, everywhere silicon in 10 lakh, and out of 10 lakh, there are only, you can say, one atom where the one silicon atom out of 10 lakh atom has been replaced by the phosphorus. And imagine only this much amount of replacement or doping can create a lot of difference in the conductivity of that material. So you keep on playing with this doping level, and then you keep on changing the properties of the resultant extrinsic n-type semiconductor. This is this 10 lakh is, suppose I give another example. Suppose you imagine entire population of the entire Mumbai city as a silicon. All are silicon atoms. Then you just add 10,000 people bringing from some other planet or some other city, and then uniformly distribute them. Imagine how low this or how dilute this concentration is. But still, those 10,000 people in so many, you can say 1.4 billion, they makes a lot of difference. Even if the distance is large, even if they are located at any distance, very, very far away from each other, but still they make a difference. So now the same thing. So initially, when it was intrinsic, so there was a conduction band and there was a valence band. Now if you add donor, so this donor will add actually certain levels which are not actually in the conduction band, below the conduction band, but very near to. This distance is relatively, it is looking quite large, but it is actually very, very near to the, you can say, conduction band. It is so near that at room temperature, all these donors donate their, means all the electrons are, these donor electrons are in the conduction band in n-type of the, you can say, semiconductor. So similarly, like it was the donors. Now similarly, there is acceptors concept. So suppose I add boron. So boron has, we know, 3 electrons. So now one boron I place in place of those 4 spheres. I remove the top sphere, and there the red sphere I replace with one boron. Now what will happen? See, boron has 3 electrons and all silicons has 4 electrons. So one, you can say, in that case, there will be, the 3 electrons will be bonded. However, there remains an additional electron, which can be accepted at that site to make 4 covalent bonds. So like 3 bonds are already, you can say, made. One is, so it is like here. So now you have silicon. There are 4 everywhere. Now there are in boron, we have 1, 2, 3, 4. Three were only there. So this is actually left vacant. So what it can do actually, it can accept an electron which is somewhere moving around, and that it can accept that electron and make it this octave complete, octet complete. So in that case, it is actually, you can imagine, it is ready to accept. And this situation where electron is absent is called as the hole. So this is a concept of hole. So this, you can call it a positive charge also, because it can actually accept 1 electron. And this is called as the p-type of semiconductors. If we add boron as a semiconductor. Now this hole, it is ready to accept 1 electron. If electron is moving somewhere, or see, this is also, there are so many other, this is a part of a lattice, infinite lattice, and so there are other atoms also there. So it can accept the electron from the nearby silicon, which is, though it is actually completely filled. There are silicon, all 4 are silicon, but if it can accept 1 electron from all those 4 silicons, so though it will become octet here, now this vacancy which was here will move from this point to that point. So now though there is no boron. However, there is a vacancy because one electron from the silicon bond has moved to this particular boron. So there is one animation. You can just see how the hole is moving. So this was boron. So initially hole was here near to the boron. Now an electron from this silicon has come to this place, and the boron, the hole has moved from this. Now the electron from this to move to this, and you just watch for few seconds how a hole is moving inside a lattice. And you see, though hole is here, at some other place where there is no boron, but hole is still existing because it has moved from the boron site. Just see. Just see and try to visualize. Okay, so this is now the movement of hole. So movement of hole is generally it because see it moves slow. The mobility for holes is slightly less compared to the electrons. And ultimately, if you see, it is only electrons which are moving, because the electron has moved from one place to another. As a result, the electron, the hole has moved in the opposite direction. So now let us see different kind of dopants which are. I will remove this. So different kind of dopants which we have. In two examples, we learned that we can use phosphorus, we can use boron, but there are other dopants also which can use. So there are different, and those dopants can produce a level which is, if it is N-type, the level is below the conduction band. If it is P-type, the level is above the valence band. So if you dope, like we have doped with the phosphorus in our first example in just 2 slides before. So if we add by phosphorus, in that case, and I am having silicon which was having a band gap of 1.12 electron volt, in that case, if I dope with the pure phosphorus only, the energy level which will be created, only one energy will be created for one species. This you remember. So it will be 0.045 electron volt below this conduction level. So if you dope with the phosphorus, if you dope with the entire lattice, entire infinite lattice with only one phosphorus, so you will have the entire conduction band, continuous conduction band, and inside the whole, you can say, crystal, only one level which is just 0.045 below the conduction band. If you have, if you add 10,000 phosphorus atom, then there will be 10,000 unique levels around just 0.45 electron volt below the conduction band. So now you can decide which kind of property you want from your device, or what kind of extrinsic semiconductor you want, which level you want, which level will be optimum for you, that you can find out by different calculations or your theoretical background. So okay, I want that my level should be 0.25 electron volt deeper to the conduction band. In that case, my this device will work in certain fashion, which you have actually designed. So suppose you want to have a level which is 0.25, then what dopant you will choose? You will choose the dopant of carbon, which will generate an energy level exactly 0.25 below. You can choose the platinum also. Now, if you have both carbon and platinum, then you will choose better. How you will choose the better one? There are many other things actually. You just cannot put any dopant inside any lattice. There are many restrictions also, because this is a foreign atom inside to the lattice, so it will create the strain inside lattice also. So you will have to take care that part also. If there is not, it is not disturbing the entire lattice, because if you change the lattice, entire lattice, the lattice parameters will also change, and if lattice parameters will change, your accordingly your energy levels will change, because the solution of the Schrodinger equation will accordingly change. Because the potential, periodic potential, the width of periodic potential or the height of periodic potential will change if you strain. Therefore, if you depending upon your application, whatever you want to fabricate or conceptualize, you can choose different dopants. In normal, like our electronic devices, more than 95, or I can call even more, the p-type doping is done by phosphorus, and boron is used for the p-type doping is done by boron, and phosphorus is used for the n-type doping. And you see the levels are exactly similar. It is 0.045 below the conduction band, it is 0.0545 above the conduction valence band. So by these are some dopants which I explained here. Now there's another concept of degeneracy and non-degeneracy, or generate or degenerate or non-degenerate semiconductors. So if the electron or hole concentration, so if you are like you are adding, see, as I said, out of entire lattice, if you have added only one phosphorus, you can keep on adding, and you can make at every site of you can say every octahedral site, or in our case tetrahedral site, you have added one impurity. So you will keep on adding the energy levels. If the electron or hole concentration is much lower than the effective density of states in the conduction band or the valence band, then it is called as the non-degenerate semiconductors. The Fermi level is at least 3 kT above the top of the valence band, or it is 3 kT below the bottom of the conduction band. What is the Fermi level? Fermi level is a, you can say, energy level. Normally, in case of metals, it is defined as the top level, which is filled at the 0 Kelvin. However, in case of semiconductor, because the top level is at the, you can say, top of the valence band, so and from valence band to the conduction band, there is totally forbidden level, forbidden states, and then there is a conduction band. So in case of those things, you can define at 0 Kelvin, the probability of this is exactly half. Probability of filling this level is exactly half. Then this was non-degenerate, when you are having almost very low. The degenerate is when the doping concentration become equal or larger than the corresponding effective density of states. The semiconductor is referred as the degenerate semiconductor. For very heavily doped N-type or P-type semiconductors, EF will be above EC or below EV. So, it was like you have a conduction band, and we realized that when we dope by, you can say, phosphorus, an energy level is created 0.045 electron volt below the conduction band. However, if we keep on adding the phosphorus, and it is more than the effective density of states available there in the situation, what will happen? It will become almost a continuum, and the valence band will shift. Conduction band will, you can call that itself is a conduction band there. And then when the conduction band, when an entire thing is filled, you have a lot of electrons, the conduction band you can shift little bit, and then the Fermi level will obviously lie inside the conduction band. Just imagine. Similarly, if you have more P-type semiconductor, that also you keep on adding more and more and more on more impurities. In that case also, in case of highly degenerate semiconductor, very highly doped semiconductor, the level will be coinciding below the you can say top of the valence band, the Fermi level. So very high impurity concentration means what? You know? So it also causes a reduction in the band gap. So for example, the typical doping density, suppose it is 10 to the power 3 into 10 to the power 19 centimeter. This I have taken from the textbook. So if the doping concentration is 3 into 10 to the power 19 centimeter cube per centimeter, in 1 centimeter, how much is the concentration of silicon? Suppose it is of the order of 10 to the power 23. So still it is out of 10,000 atoms you are doping 1 atom. So by this doping in 10,000 level, you can the band gap, which was actually 1.12 electron volt, it becomes only 0.12 electron volt. So it is only 10%. So imagine how much change you can put inside the semiconductor by changing the doping level. It was 1.12 electron volt, and out of every 10,000 atom, if you are changing only one atom, in that case the band gap will be reduced from 1.1 to 0.12 only. Now this is clear. Now we have learned degenerate, non-degenerate semiconductors, N-type, P-type also, or doping. N-type we will see once again. So now how this electron can move inside a material. There are different ways in how the carriers moves. Carrier means it can be electron also, it can be holes also, and not ions. That whole moving hole and moving ion is totally different. Ion moves inside liquid, ion some special solids also, which are a different kind of solids, which is little bit, or you can call them gel also. But in solids, only electron moves or hole moves. Hole is also, you can say, it's because of the movement of electrons only. So how these carriers can move inside a material? So there are different transport processes which are drift. By drift, and carrier can move. By diffusion, a carrier can move. Then there is also possible that the carriers can be generated. There is also possibility that carrier can be recombined. If carriers are recombined, they cease to exist. If carriers are generated, they are new carriers created. And then there are thermoionic emission also, by which it moves from one place to another. Then tunneling, space charge, and impact ionization. So by these are the all different processes of carrier transport. We'll very quickly understand each of these in a qualitative way. We are not doing any mathematical derivations because that will take too long. So we are just understanding concept wise. So what is the first is drift. We'll come to diffusion generation one by one. So what is drift? So you have an electron which is inside the, suppose let us consider it is now inside a conduction band. So inside a conduction band, it behaves like almost free particle. So it can, there you are not applying any potential. So this is free. So it can move left, it can move right, it can move up, it can move down. So little bit of that. So however, if you integrate over a period of time, maybe over a long period of time, you will see the net motion is absolutely zero in the absence of any you can say potential. So when nothing is associated, then it can have a random motion up, down, top, bottom, but it will not move anywhere. However, if you apply a very little potential from one side, so what will happen? This electron will experience a net force towards the that field, because of that field. So this I already explained. The random thermal motion of the electrons lead to the zero net displacement of an electron over a sufficient long period of time. But if you apply small electric field on the semiconductor sample, each electron will experience a force from the field and will be accelerated along the field during the time between. Now, if it is accelerating, so there are other electrons also. There are so it will collide with them also. Once you have applied a potential, the electron will start moving. It will collide with another electron and lose its energy. Then again, because the potential is already there, so again it will experience the same field. It will gain the same energy. It will start moving. So in the net, it will be accelerated in one direction. So due to this application of potential, an additional velocity component is superimposed upon the thermal average motion, which was actually zero. So this additional component is called as the drift velocity. It is start moving because there is a potential, then it strike with other carriers or sometimes other sites also, and then lose energy. Then again it starts gaining. So this net component is because this net you can say velocity is called as the drift velocity. So you can call it as an average kind of thing. So due to this, there is a net displacement of electrons in the direction opposite to the applied field for electrons. However, for holes, it will be in the direction to the applied field. At low field, the drift velocity is proportional to the electric field. This proportionality constant is called as the mobility. So learn an important parameter, which is mobility. So mu n is mobility of electron, mu p is mobility of holes. So this this comes from the proportionality constant of how it is actually moving. So if I say the total drift current J, which is this is the charge on electron or hole, and this is the concentration of electron hole, and this is the mobility, and when it is multiplied by E, and then this is the total current. This is due to the holes, this is due to the electrons. So total current is drift current is the total current due to the flow of electrons, and total current due to the flow of the holes. So drift is simple, you have understood. Then another is diffusion current. Diffusion is always related to the concentration. So if you put many of the carriers at one place, and you come after one day, or not one day, means you come after some time, and then you will find that all these electrons are uniformly distributed inside the entire material if the potential is same. So what has happened actually, suppose all the electrons were initially at the one end of my semiconductor, and after some time they have actually become uniform, the concentration has become uniform. So the electrons has moved, carriers has moved from one place to another place. So obviously, because the carriers are moved, so charge is moving. If charge is moving, there is a current, and this current has come because of the diffusion of those carriers, because there was a concentration gradient. So always diffusion takes place due to the concentration gradient. So if there is a special variation of carrier concentration in a semiconductor material, in that case the carrier tends to move from a region of high concentration to a region of low concentration. This current component is called as the diffusion current and can be given as by this. The diffusion current Jn can be given by Qdn by dn by dx is the one minute. There is some issue regarding the battery. I'll start within 2 minutes. I'll just go and call. So then it becomes diffusion current. The other is thermionic emission. It occurs when carriers in the surface region gains enough energy to be emitted into the vacuum. So with the inside there all the bonds are saturated inside a material. However, at the surface you have some dangling bonds and or unsaturated bonds also. So when an electron reaches there, there is a possibility sometimes when it gets sufficient amount of thermal energy. So then this can actually emitted into the vacuum level. So carrier has moved from the semiconductor to the vacuum, and this kind of transport is called as the thermionic emission. Then there is another process that is called tunneling. Tunneling is when you have a very high barrier, which in normal situation the electron cannot penetrate. However, there is a since it is in a wave and it keep on striking on that barrier, at every strike there is a finite probability, though it is very low, very feeble, but still if the number of attempts are very high, in that case it can tunnel through that barrier. So in a physical scenario, if we try to explain that in the summary, you have a ball which is hitting the wall, and we know it very well that this ball can never cross, never break the wall and appear on the other side. However, when in quantum mechanics, the electron, there is a finite probability every hitting that this can appear on the other side. So in the same, you can say, I can give here also that ball, when it is hitting the wall, there is a possibility, very finite but very low probability, that it can, you can say, pass through the wall without breaking the wall. That is called as the tunneling. So electron actually it is hitting, it will never break the, it can never break the wall or that barrier, because it doesn't have that much energy, it doesn't have that much strength. But every strike has definite probability, and though it can tunnel through. So that kind of thing is, that processing or that is called as the quantum tunneling. And then there is a space charge limited current when the injected carriers are not compensated by the ionized impurities in the semiconductor. So space charge carrier is actually you are inserting carrier injection. space charge limited conduction happens because of the carriers are injected from the electrodes inside that. So these are not actually, so you have now more carriers inside the material. The other processes are impact ionization or avalanche process. What happens when an electron start moving and you applied very high potential, it will gain certain amount of energy proportional to the potential or proportional to the field. If the energy is so high that this electron can strike to the nearby, you can say, atom, or it can have that much high energy that it can break a bond and release that electron. So if it break a bond, or this electron, if it break a bond, then in that case it will create an electron hole pair. So now effectively you are having two electrons and two holes. If earlier there was one electron and one hole, now we are having two electrons and two holes, and the potential is same. So both of them now start moving with the same same speed or same energy, and they will strike further. So this multiplication takes place manifold, and you will have a lot of current inside the device. This is called as the avalanche process, and this process is important in PN junctions, and a important device which is called as the Zener diode, which is very important and used to regulate many of the you can say used to regulate the potential inside many of the electronic circuits, is made on the principle of this avalanche process. And this is in the Zener diode, that is in the reverse bias region. So I will once again repeat, the high field accelerate these new electron hole pairs which collides with the lattice to create more electron hole pairs. As the process called impact ionization or the avalanche process continues, the PN junction breaks down and conducts the large current. So now we'll just try to see the difference between what are p-type and n-type semiconductors. So you have this is a extrinsic intrinsic semiconductor, where you have valence band, conduction band, Fermi level at the center, and there were 4 electrons which are excited from the valence band to the conduction band. You can say that thermal excitation. So now 4 electrons are there in the conduction band, so you will have 4 holes here in this one. So now this 4, suppose I consider this as a 1 centimeter cube volume. So now my concentration of N, or electronic concentration, will be 4 per centimeter cube. Similarly, electrons are here, so it will be 4 centimeter per cube. Here also it will be, the whole concentration will also be 4 centimeter per cube. So my thumb rule is like that: the concentration of electrons and concentration of hole are same, and these are equal to the concentration of here in intrinsic case. So now here it is N into P is equal to Ni, and if you multiply them N into P, then it becomes Ni square. So this concentration is this is intrinsic. So now few you can say levels we can once again see. This is EC, that is the bottom of the conduction band. This is EV at the top of the valence band, and this is the width of the conduction band. And suppose it is near to the vacuum level, so the difference between the EC and the vacuum is called as the electron affinity, and the difference between the Fermi level and the vacuum level is called as the work function. This N and P, these are the semiconductor technology. These are fabricated using the planar technology. So planar technology is used to extensively for PN junction and integrated circuit fabrication. The planar process include oxidation, lithography, ion implantation, and metallization. These are different processes while you make a device of PN junction diode. the most important characteristic of PN junction is that they rectify. Rectify means they pass current in one direction and do not allow the current in the opposite direction. So two regions of P and N type semiconductor materials that are uniformly doped and physically separated before the semiconductor are formed. So you have like P type material and you have N type material you can generate by doping. The Fermi level is near the valence band as in the P type material and in the conduction band as in the N type material. So you have like P type material, the Fermi level is close to the valence band, and in N type material the Fermi level is close to the conduction band. While N type material contains a large concentration of holes with few electrons, the opposite is true for the N type of materials. Now these are two I have made N type material and I have made P type material. Now what happens when I try to join them? So this was like P type material, this was N type material. Now what will start as you join them, as soon as you join them, the electron starts to flow from this side to this side and they start combine with the holes, and so this is what this is called. This is because of the you can say concentration gradient. So what we will call it? Which current we will call it? So it is diffusion current, because this side there are more electrons and this side the concentration of electron is more, this side the concentration of hole is more. So electrons will move from higher concentration to lower concentration. So this will called as the diffusion current, and this diffusion current will keep on continuing until there is another process which takes place which actually stops it. Now if we see that electrons are flowing from this side to this side and one electron moves from this side, a positive ion is actually generated. So there is a net potential, and this is the, you can see this. So net potential is, as the electrons are moving from this side to this side, the net potential is actually increasing. So this side it is become positive. So as soon as it becomes positive, it will start attracting the electrons. So after some time, because of the, and this is because of the you can say development of the potential. So this you can call as a drift also. So because of the drift, it will start pulling electrons from this side to this side, and because of the diffusion, electrons are moving from this side to this side. Opposite is true for the holes also. So these two processes will compete in the beginning, but after a certain time they will become an equilibrium. And under the that equilibrium is called as a thermal equilibrium. So under thermal equilibrium, you find this will come under thermal equilibrium, this space. So at thermal equilibrium, that is the steady state condition at a given temperature with no external excitation, the individual electrons and hole currents flowing across the junctions are identically zero. So neither in that case electrons are moving from this side to this side, or nor hole are moving from this side to this side. However, in this situation you see an static, a built-in potential is actually generated here. So thus for each type of carrier, the drift current due to the electric field must exactly cancel the diffusion current due to the concentration gradient at the thermal equilibrium. Now let us see another thing is that is generation. 10 minutes already. So that is generation and recombination. So in thermal equilibrium, the relation Pn is equal to Ni square is always valid, where P and N is the density of electrons and holes, and N is the intrinsic carrier density. If excess carriers are introduced to a semiconductor so that Pn is greater than Ni square, we have a non-equilibrium situation. The process of introducing excess carriers is called as the carrier injection. Now carrier injection can be done by many ways. So most semiconductor devices operates by creation of charge carriers in excess of the thermal equilibrium value. We can introduce excess carriers by optical excitation or forward biasing a p-n junction. You can do in a p-n junction, if you illuminate it with a certain frequency of optical excitation, in that case electrons and holes will be generated. So whenever a thermal equilibrium condition is disturbed, that is when in thermal equilibrium condition it is always Pn is equal to Ni square. So there are actually many situations where problems need to be solved. Always remember, we will not be doing in this course, but if you want to go ahead and learn in advanced stage, in that case always remember that in thermal condition you will have to start with a situation where P into N is equal to Ni square. This is the way you find out the carrier concentration in using different dopants. So so what happens when the thermal equilibrium condition is disturbed? The processes exist to restore the system to the equilibrium. And what is equilibrium? That is Pn is equal to Ni square. In the case of injection of excess carriers, the mechanism they restore equilibrium is recombination of the injected minority carriers with majority carriers. Depending on the nature of recombination process, the energy released from the recombination process can be emitted as a photon or dissipated as a heat of the lattice. So it can be either photon, when it is emitted as photon, or it can be it can emit a phonon, and phonon it can provide you heat to the lattice. When a photon is emitted, the process is called as radiative recombination. Otherwise, if a photon is not emitted, the emission process is called as the non-radiative recombination. So there are two kinds of recombination. One is radiative recombination and another is non-radiative recombination. So this is in a very you can say small picture I try to explain the generation and recombination. So a photon falls here and electron from this level, from valence band, electron excited to the conduction band, and then this is called as the generation. So it is generation, and this light is absorbed. Now this generation can also happen if this level is close to each other, EV and EC, and thermally also the electron can be excited from the ground level to the excited level, valence band to the conduction band. Now when they cannot stay for a long. When you excite an electron from valence band to the conduction band, it can come back to the valence band, and when it comes back to the valence band, the same amount of energy which it absorbed while going from valence band to conduction band will be released. So if it come back from this point to this point, this much energy will be released. This can be, if it is coming directly, it can come following different intermediate levels also. If that energy is in the range of photon, then it will be called as a radiation, radiative recombination. Otherwise, it will be non-radiative recombination. So it is thermal, you can say, generation. Similarly, it can be thermal recombination also, where phonons are emitted, and then it is a radiative recombination. So it can be. So recombination phenomenon can be classified as direct and indirect processes. Direct recombination, also called band-to-band recombination, usually dominates in direct band gap semiconductors such as gallium arsenide. And this is how I have explained. So this is direct band gap material. So electron, it is a photon. So from the conduction band, an electron falls to the valence band, and a photon is emitted. However, in case of indirect band gap material, so first what happens, like in silicon, the P value is different. So this electron, first a lattice interaction will take place, it will absorb a phonon. So it will absorb or emit also. So it will, in this case, suppose it is emitting a phonon, and then by emitting a phonon, so this is, by emitting a phonon, the energy is actually coming down. If it is absorbing a phonon, it will come here, this side. So by doing, but by doing this, actually it is changing its P value. So now it comes here from this point, always these transitions, the optical transitions, these transitions are in this direction, in y direction only. So then it will be emitted. The same thing is explained here in a detailed way. You can go through it, and if you have any doubt, you can email me. I will be. So indirect recombination via band gap recombination centers dominate in indirect band gap semiconductor, which are such as silicon. So for indirect band gap semiconductors such as silicon, a direct recombination process very unlikely, because the electrons at the bottom of the conduction band have non-zero momentum with respect to the holes at the top of the valence band. A direct transition that conserves both energy and momentum is not possible without a simultaneous lattice interaction. So therefore, dominant recombination process in such semiconductor is indirect transition via localized energy states in the forbidden energy gap. These states act as a stepping stone between the conduction band and the valence band. So it was same thing. Now, once you have excited an electron, and by giving, you can say, by illuminating it, so the electron goes into the excited state. So it cannot remain very long there. After some time, it falls back to the ground level, or in present situation, it falls back into the valence band. So if you are exciting an electron from valence band to conduction band, it cannot remain endlessly there, it falls back here. So the time up to which it remains there in the conduction band, that is called as the lifetime of that carrier. So if you excite an electron, it goes to the, if you illuminate or you provide an energy, sufficient energy where electron moves from the valence band to the conduction band, it remains there, and after some time it comes back. The time is, the average time which it stays there is called as the carrier lifetime. And how do we measure? That is a very important parameter for the device applications. How much is the carrier lifetime? So how do we measure this? There is a standard experiment you may be doing, some of you may be doing at some stage. So you have a semiconductor, so you illuminate this semiconductor with a light pulse. As you illuminate with the light pulse, the frequency of the light should be so high that energy is sufficient so that it can raise an electron or all electrons from the valence band to the conduction band. Now you have a semiconductor, just put a semiconductor and electrodes from both sides, and then apply some potential. With that potential, since it is a semiconductor, when there is no light, there will not be very, there will be very, very small current. There will be very minimum current. But as soon as you start illuminating, the electrons will move from the valence band to the conduction band, and then you will have a lot of current. All those electrons which are there in the conduction band, they will start moving, and you will have a lot of current. So now it is a situation where the electrons are in the conduction band, or they are illuminated. Now at this particular point, immediately you switch off. So as you switch off, the carriers, some carriers will start recombining. So, and those carriers who have not recombined, they will be, you can say, swept away by the potential. So there will be current. This current will slowly start to decreasing. So this curve, by shape of this curve, you can find out the carrier lifetime. So this is the typical lifetime of the carrier lifetime. So now I come to the another important point, which is the semiconductor metal semiconductor contact. So there are two types of metal semiconductor contacts, the rectifying and non-rectifying or ohmic contacts. The first practical semiconductor devices was the metal semiconductor contact, where a metallic whisker was pressed against the semiconductor to make a point contact rectifier. It was proposed that the rectifier behavior could arise from the potential barrier as a result of the stable space charge in the semiconductor. The model arising from this concept is known as the Schottky barrier. Metal semiconductor contact can also be non-rectifying, where the contact has negligible resistance for both polarities. The type of contact is called as the ohmic contact. Ohmic contact is when you apply a voltage and measure the current, and this current is independent of the polarity. In positive side also you are measuring the same current, in the negative side also you are measuring the same current. And if you you can say sweep the voltage and the curve is like a straight line from both the sides, then you can call it as a ohmic contact. However, all semiconductor devices, always the integrated circuit, need ohmic contact to make connections to other devices in the electronic system. So now if we make a metal semiconductor contact, let us consider the one-dimensional structure of the metal semiconductor contact, the energy band diagram of an isolated metal and isolated, I have few more slides. So if you have a semiconductor and you have joint with the metal, so if you apply a potential here, so why it will behave like a rectifier or Schottky diode, it can be explained on the basis of the band diagram. So you draw a band diagram where this metal which you have added here is placed here, and then this semiconductor, the band diagram of this semiconductor is you have drawn here. So in case of metal, you always have a work function. So this will be from the vacuum level. Suppose work function is phi m, you will have q phi m this level, and then it is in the case of semiconductor you have electron affinity. Electron affinity is suppose q phi, q chi, and then when you join them, so at the time of joining you have to always remember few things. So this work function is different to this electron affinity. Or this is work function of the semiconductor. So because there is a difference, this difference is the reason of why there is a, you can say, barrier is created. So this work function is energy difference between the Fermi levels of the vacuum level. So this I have already explained, the electron affinity. So when metal makes intimate contact with the semiconductor, the Fermi levels in the two materials must be equal in the thermal equilibrium. Now in this situation they were actually separated. Now if you bring them together, there are certain rules which you have to follow. So first is that when they make intimate contact with each other, the Fermi level of both the materials always, even if you are making heterostructures, then also the Fermi level should be equal. They should be in thermal equilibrium. They should be equal in thermal equilibrium. In addition, the vacuum level must be continuous. So this vacuum level, their vacuum level cannot be abrupt. So these two requirements determine a unique energy band diagram for the ideal metal semiconductor contact. So for this ideal case, the barrier height, this barrier height. So it is so how much is the barrier height is the difference between this level and this level. So it should be like this. So if you see now, if something is moving from the electron side, a barrier has been actually created. So for the ideal, the barrier height is simply the difference between the metal work function, which was heat, and the semiconductor electron affinity, which is like this. This is semiconductor. So this much difference, a barrier has been created, and this barrier is actually a cause of the Schottky, behaving it like a Schottky barrier. So now if you see this plot for the silicon, if you have different kind of metals, if you add, you will get the barrier height of you can say different level. So suppose I use gold and I make a contact gold with the silicon, I will get the barrier of how much barrier of approximately, this is the gold, this is my silicon, so I will get approximately 0.7 EV barrier. So that means you can see if there is a barrier, it will be obviously rectifying. If the electrons are in one side, electrons are moving from right to left, then they will not face any barrier. However, when the electrons are moving from the left to right, they will face a lot of barrier and they will not move. So it will not allow the electrons to move in one direction, and it will allow the electrons to move easily from the other side, and this is called as the rectifying behavior. Now we see another important structure that is called as the heterojunction. A heterojunction is an interface between two layers or region of dissimilar semiconductors. If the semiconductors are not same, they are dissimilar, then the interface of those two we can call as the heterojunction. So these semiconductor material need to have unequal band gap as opposed to the homojunctions. It is possible to engineer the electronic energy band in many solid state devices applications, for example semiconductor, lasers, solar cells and transistors. The combination of multiple heterojunctions together in a device is called as the heterostructure. Although the two terms are commonly used interchangeably, a heterojunction device is formed by depositing a large band gap semiconductor epitaxially on a small band gap semiconductor. The common elemental semiconductor are silicon and germanium. Common semiconductor compounds such as gallium arsenide, indium arsenide, indium antimonide, etc. So now we are moving to the semiconductor devices. So integrated circuit and electronic discrete components such as diodes and transistors are made of semiconductors. Silicon forms most integrated circuits. The semiconductor devices are the foundation of the electronic industry, which is the largest industry in the world. To date, there are about 20 major devices with over 150 device variations related to them. All these devices, all the semiconductor devices, or all this kind of devices, they can be constructed on the few device, on the basis of few device building blocks. If you make few device building blocks, all the devices contains that. So there are four kind of device building blocks. I will explain very quickly one by one. See, all the semiconductor devices can be constructed from a small number of device building blocks. These are, number one is metal semiconductor interface. Metal semiconductor, so in this you have a metal and you have a semiconductor. You have added metal to a semiconductor, and obviously because of this addition there will be a barrier, and that barrier will depend upon the work function of this metal, how much is the barrier height, and then the electron affinity of the semiconductor. This will show whether the electrons will be moving in which direction. So this is the first building block. And then there is a next building block, which is the p-n junction diode, in which a p-type and n-type materials are formed. This junction is a key building block of the most semiconducting devices. So in this you have a p-type semiconductor and you have n-type semiconductor. You join them together as we saw there in that, and we will see in next class also where the photovoltaics, we will learn photovoltaic. That is also solar cells are also p-n junction and how they work. So the second building block is p-n junction. Now we will go to third, that is the heterojunction. Heterojunction is means in this p-n p-n junction the semiconductors are of same. So when you have two different kind of semiconductors, so this building block is the heterojunction interface. That is an interface formed between two dissimilar semiconductors. For example, we can use gallium arsenide and aluminum arsenide to form a heterojunction. Heterojunctions are the key component for high speed and photonic devices. You have one semiconductor, you have another semiconductor, and a junction is made. This is and the fourth and very important building block is the MOS structure, in which you have a metal and then semiconductor, and between metal and semiconductor there is a very thin oxide layer. So in MOS structure, the structure is considered as a combination of metal oxide interface and oxide semiconductor interface. By using the MOS structure as the gate and two p-n junctions as the source and drain, we can form MOSFET, field effect transistor. The MOSFET is the most important device for advanced integrated circuit. Because of the lack of time, last few slides I have run quickly. So I request you, all of you, to go it carefully. I am always available. If you have any doubt, you can ask me. You can send me an email or you can ask me on phone also. So now last two slides, that is the invention of major semiconducting devices. So metal semiconductor contact was invented in 1874, then light emitting diode 1907, bipolar transistors 1947, PN junction 1947. This is the like year wise how we have progressed from a simple metal semiconductor contact which has given you given them a rectifying behavior, and now we have reached up to the MOSFET level where the transistor size is only up to 5 nanometer. है ना? And even more. And some technologies which are important semiconductor technologies which have grown over the period of time. There is Czechoslovsky crystal growth, which we will see in the 6th or 5th lecture, how to grow the single crystals using this method. Then Bridgman crystal growth. Then this is the growth, this is the mixing of 3rd, 5th compound, that is also crystal growth. Then diffusion, lithography, photoresist, oxide masking. These are very crucial, important semiconductor technologies which have actually enabled the advanced systems to generate, or even like today we are seeing such a the very even mobiles and all those things they are possible only because of the development of technologies at such a fast pace. I think with this, I end the talk. Uh, if you have any question, you may ask me. So now there is one announcement. Actually, because of the elections in Maharashtra, there is a holiday on 20th. So the class of 20th has been shifted to 28th of November at the same time. So now there will not be any class on day after tomorrow, and we will have next class as scheduled, and the class of 20th November will be held on 28th of November. Well, if there are no questions, then thank you. See you in the next class. Bye.